Thank you very much for inviting me here. It's a pleasure also to see some of the people I know since a long time. So this is going like that, huh? Okay. So it's now some years that I am struggling with the amazing realm of the interactions between living beings and the physical, non-living environment. And so I will offer you a couple of examples, very simple examples of this. In fact, almost metaphors or very crude examples. But before doing that, I just want to show you, some of you probably know it already, is the Naturgemälde, which is a drawing, one of the many versions of a drawing made by Alexander von Humboldt, who was the inventor of the modern concept of nature. At the beginning of the 19th century, he interpreted nature as not as a machine, as it was done before with the mechanicism, but rather as an ensemble of connected cycles and interactions. So this is a very modern view. And then from there, all the study of the interactions, for example, between climate and living beings or environment and biosphere started. So there are various people who address this problem. Humboldt is this one, lower right. But for example, Alfred Wallace, who is a co-developer of the evolutionary theory with Darwin, defined Earth as one grand organic whole, which is pretty interesting. The pensive person up there is Vladimir Vernadsky, who was the inventor of biogeochemistry, basically. He published in 1926 a book in Russian, which was called Biosphere. And it was translated almost immediately in French. It was translated in English only in the 70s and 80s. So it's really the precursor of what was done, for example, by James Lovelock, who with the Gaia hypothesis is, of course, we can discuss a lot about that. But the important thing is that the attention to biogeochemical cycles started from this work, and the whole domain of Earth system science started from there as a complex system. And up there is Lynn Margulis, who was a great biologist, and then was co-working with Lovelock on Gaia, but on many other things like mitochondria and other things. So I will, if I go too long, just open the hole and I will fall down. I mean, just stop me. But I will talk about the role of environmental stochasticity and then vegetation and climate, and maybe a little tour to the habitability of exoplanets. So the first thing is how the geosphere is affecting the biosphere. We all know that is Köppen zones. I mean, how climate affects the biosphere. This is studied in elementary school, but there are ways in which the geosphere can affect the biosphere, which are not completely, there is something interesting that comes out. I mean, are not completely expected. So for example, take this model. This is the host parasitoid model. It's a Beddington version of a famous model, which is the Bailey model, but basically it's two coupled maps. One is the parasitoid, I mean the poor bug, the poor caterpillar, and then the host, and then there is the parasitoid, P, which is the wasp typically that puts the eggs in the caterpillar and uses the caterpillar for food for the larvae. This is a system that can display the usual things. I mean, this is a bifurcation diagram, for example, for the parasitoid. And then if you stay in the chaotic region, you see something like that, the time series of the host and the time series of the parasitoid. But then let's say that maybe we can now allow delta. Of course, you don't need that term, right? But you allow that term to be variable in time, random white noise. So it's a parametric noise. It's not an additive noise. So if you do that, what you see is that there is the emergence of on-off intermittency, which is one of the many forms of intermittency, and it's defined as more or less, suppose you have a system when there is an equilibrium, let me call an equilibrium, can be a fixed point, a limit cycle, a chaotic attractor, whatever, whose position in phase space depends only weakly on the control parameter, but whose stability does depend on the control parameter. So if the control parameter varies, the position of the equilibrium does not vary at all or much. Well, I mean, in that much, there is a lot of discussion to be done, but its stability does. So you spend long times close to the equilibrium, but sometimes you are just shot away because you are getting an instability. And then you come back. So you see, this looks like heavily non-stationary. So if you look at a limited portion of time, it can look as a non-stationary signal, but it's on the long time stationary. I mean, the statistics is well defined. So again, stationarity or not, it depends a lot on the length of the time series you are considering. The interesting thing is that this is the host, so we allow let's say the grazing, the reproduction rate of the host to vary, for example, for weather, for climate, or whatever. And then this is the distribution of the durations of the off phases, which in very simple systems like the logistic map are, it's a duration to the minus 3 halves, Eggy et al., Eggy, Plattenspiegel. I mean, it can be computed very easily. This is not exactly the same thing, but it's, again, a sort of a power law-ish long tail dependence. So it is on-off intermittency. The other interesting thing is that if you couple the maps, let's say 100 maps, with periodic boundary conditions of the host, but the parasitoid that can fly here and there is just one map. So the parasitoid goes where the host is because it can fly. Then you have this kind of spatiotemporal intermittency, and this is the time series of the parasitoid, chaotic but not particularly intermittent, while each of the positions on the network has an intermittent behavior. The interesting thing is that sometimes you have non-intermittent dynamics, but if you couple the host, you get intermittent dynamics, and vice versa. If you have intermittent dynamics in a single map and you couple them, you don't have them. So you don't have intermittency. So it's a very rich system. But this means that bursts or eruptions in host populations, for example, can be mimicked, rationalized with such simple description. Same thing happens also for ODEs. A priori, that was expected but not totally obvious. This is a 3-species food chain, not a network, and so it's a let's say it's a predator on a grazer and on a resource, and then again in the chaotic domain. And then also for this, you have basically intermittency, not in the predator, but in the herbivorous component, and of course also in the resource. And this is the way that control parameter is varying in the course of time randomly. Okay. So this is just to tell you that if you have a little bit of random variability in one of the control parameters, totally random, totally wide, you can have a very complex dynamics. Now we go to the other limit. I mean, if we look at how the biosphere can affect the geosphere, I mean, the climate, and then there's plenty of things here that one can do. So we do just a brief introduction and then a very simple example. There's a two-way feedbacks. I mean, organisms adapt to their environment, evolve in order to, let's say, well, to be fittest or something, or fitter, but they also change the environment. And for example, the so-called ecosystem engineers is a term that was invented in 1994 by Moshe Shahak and co-workers. It's like beavers. I mean, beavers change a valley in a lake. They do that in order to protect themselves from terrestrial predators, wolves, foxes. But in doing so, they change completely the environment, and they change the selective pressures, I mean, the predation pressures also on other organisms that are there. Same thing for the plants in the desert. In area where there is very low precipitation, typically shrubs become islands of moisture and fertility, and so favor other species. Of course, they don't do that in order to favor other species. They do that in order to right, just to survive. They were selected in order to survive. So this is interesting because it's another way of transmitting, let's say, information, because in some way it's through the modification of the environment. It's like leaving a big bank account to your siblings or not. So the siblings of these beavers that are already in a lake have a simpler life, so to say, than the first generation. Of course, this is also selected evolutionary. I mean, this is also a product of the evolution and genetic selection, but it goes through another path. Niche construction, exactly what I was saying. So many organisms construct their own niche. And then you go to larger and larger scales, complex adaptive landscapes. The landscapes you see around are generated, most of them, by the interaction between physical forces, erosion, sedimentation, and so on, and biological forces. The patterning of the vegetation in the desert is also affecting the way sediment is transported and deposited. And then you go to the big picture and you have the global biogeochemical cycles. I mean, you know that the atmosphere has oxygen because there are living organisms. There would be no oxygen without the biosphere. And the carbon cycle is dominated by the biological branch, and so on and so on. Nitrogen cycle, and so on and so on. So I do a very simple example, right? This is the nice thing. Then we do a very little thing. This is Charney was one of the founders of modern meteorology. He was the first one who did the first successful meteorological prediction in the 50s using ENIAC and MANIAC, that were the two computers at Los Alamos. And the interesting thing is that Jules Charney did that because not he had a lot of computer power, but because before he simplified the equations going from what is called the hydrostatic, the primitive equations that are full of instabilities, it could not be integrated with those computers, to the quasi-geostrophic approximation, which can be integrated with those computers. So there was a step in mathematical simplification before using the computer. So anyway, in 75, he proposed this mechanism, which is interesting. Suppose you are in the desert vegetation is limited by water. So you have less vegetation at some point, but vegetation is usually darker than the sand. So it has higher, the sand has higher albedo. It reflects more light than the vegetation, right? Incoming solar radiation. So if you have less vegetation, you have higher fraction of light that is reflected, so it does not heat the ground. So you have a lower soil temperature. And so you have a column of atmosphere which is more stably stratified. And so you have less convection, less precipitation, and then you have less vegetation. So this is a typical positive feedback loop, which in fact is more complicated than this because it's not directly what's happening there, but it's really changing the pressure difference between different places and changing the monsoons. But this works, for example, in the Sahel. There are various experiments, not in reality, but in silico, that show that it's a mechanism that could exist there. But there is another one, which is that you lose water from the soil by two mechanisms. Evaporation, fast, very intense, but only the 5 centimeters of the topsoil. So once it's gone, it's gone. And transpiration, slower, but can reach 2, 3, 4 meters. So you have less vegetation, you have lower transpiration. So again, you have more stability in the atmospheric column. You have less moist enthalpy, or as the meteorologists say, equivalent potential temperature, which is a horrible term, but that's what is used. And so you have lower convection, lower precipitation, and so on and so on. So what we did We looked at the continental, the hydrological cycle on a continent, on land, and typically with a little model, soil dynamics, vegetation, and atmosphere, just a little box for the atmosphere, moisture coming in from the ocean, the Atlantic, if you think of Europe, and then it's going away. So it's local convergence, and then goes away, and there is the recycling of the water. How much recycling of the water you have? Well, at the global level, on the whole planet, it's only recycling, right? If you go in your garden, it's no recycling, basically. Okay. And then we were motivated by the drought in 2003, the big summer heat wave that was caused by two conditions: anticyclonic conditions, that is very little water coming in, of course, but not only that, very little recycling because the soil was very dry at the beginning of summer. And it seems that you need both things, very dry soil and anticyclonic conditions. So we did a very simple model with temperature and moisture in the soil, temperature and moisture in the lower part of the atmosphere, which is called the planetary boundary layer, and then vegetation. I mean, the equations are just derived from the standard equations. But the interesting thing is that the system has two stable points. This is the initial soil moisture. This is the initial vegetation cover. And then if you have enough soil moisture and enough vegetation cover, then you end up in a normal summer, wet and cool, whatever cool means. But if you have very little soil moisture or too small vegetation cover, so too small transpiration, you end up in a drought, in a heat wave. Of course, this is just a very simple model, but people did the same thing with bigger models that give the same result. But since they are bigger, people tend to believe to those. Okay, well, this is really just a guide for understanding. The interesting thing is that if you allow the input of water to vary randomly during the course of summer, then you have typically, for a long time, the perpetual summer, you have two, this is the probability distribution, this is vegetation cover, not the initial one, but what you get. And this is the soil moisture, what you get. Basically a bimodal distribution, where most of the summers are with the wet and with a good vegetation cover, and some of the summers have much lower soil moisture and slightly lower vegetation cover. And all climate change is here in the relative intensity of these two peaks. Both peaks are there, but the relative importance is related to the conditions that the continent is experiencing. Now this opens a little bit the issue, because some of the things I was showing, or the pattern of the vegetation, are at very small scale. Now climate models, either at regional scale or at global scale, have a resolution of the order of 20 kilometers, 10 kilometers. But you know that in 10 kilometers, the ecosystem changes completely. The patterns I'm talking about may have a size of 100 meters. So really, what is being done now is that you have the climate model, I mean, the atmosphere, ocean, and so on, and a large-scale vegetation model, which is really a green mold that you put everywhere. And then you have these interactions. But in reality, what happens at the level of the ecosystem is at much smaller scale of tens of meters, hundreds of meters. And so this is somehow done. People can downscale the climate information, but what has not been done yet is how you upscale the instabilities, the bifurcations, the change in behavior of the small-scale ecosystem. Can you build large-scale vegetation models that are sort of effective mean field models derived from that? Nobody has done that yet. Okay. Now we're going towards the end. Let's try to become even grander. And you know that thousands of extrasolar planets are being discovered, have been and are being discovered, many of which are rocky planets of the size more or less of Earth, more or less at the right distance from the stars. So what we can ask, can we say something about the climate of these planets? Can we say something about the possibility of these planets to harbor life? Which life? Okay, life as we know it, which means we need a polar solvent, water. The idea of NH4 is basically abandoned, but water is the important thing. Carbon, not silicon, because you see big molecules of carbon also in interstellar clouds. So let's say carbon and water. So basically you want to have liquid water. So the conditions for the habitability is very conservative. What are the conditions for which you can have liquid water on the surface of these planets? And of course, it depends on the brightness of the star, on the distance of the planet from the star, but also, this is what the astronomers do, that's fine. Earth is in the habitable zone. But then we know that if you have more or less CO2, the surface temperature is very different. So it depends also on the atmospheric composition, on the climate, on the pressure of the atmosphere, on the density of the atmosphere. Venus is very dense atmosphere with a runaway greenhouse effect and so on and so on. So what we started doing with friends from the Astronomical Observatory of Trieste and other places is to use a very simple model, which is an energy balance model, very simple, first principle of thermodynamics, in which you have the temperature of the planet, the surface temperature of the planet, the stellar input, the albedo, the re-emission, the infrared emission from the planet, and the transport. This is a diffusive transport across latitudes. Now, it is very simple, but the way we implement it is not that simple as it seems, because this is not sigma t to the 4, but is really the product of a column calculation from a real global model with a given atmospheric composition. So it's rather a lookup table in which the emission comes from a large ensemble of simulations. And same thing is that the albedo, it depends on the albedo of the land, of the ocean, of the ice, and various things. The albedo of Earth right now is 0.3. I mean, 30% of the radiation is reflected. But of course, if you have more ice, you reflect more. If you have more clouds, you reflect more. So it depends on that. So doing this, then the habitable zone depends, for example, as you may expect, by, this is the habitable zone, Earth is here, depends on the concentration of CO2, besides the distance from the star or the intensity. This is the stellar luminosity normalized by that of the sun. And then if you have much higher CO2, partial pressure of CO2, then you move it outside. So you have two limits to the habitable zone, liquid water zone. This is the outer limit, and this is the inner limit. And we did a lot of different simulations, 10 to the 5 different values of the parameters, for 20 initial conditions, looking at bistability, and there is bistability between snowball and warm, I mean, all these kind of things. But what I wanted to tell you here is that besides this, we started playing with vegetation and putting in this equation, which is really having a term just on the albedo that comes from the vegetation. So it's the Charney mechanism at planetary level. And then it is basically the vegetation is assumed to be darker. And for vegetation, you can use various models. But in this case, we use this three equation model, which is trees and grass. Are there trees on Kepler something? Who knows? I mean, we are playing, so to say. But trees and grasses, this is grass. This is tree seedlings, and this is the adult trees. This is a famous model because it was developed by Tillman and others in order to study a competition between different vegetation species. So basically, you have the grass stays by itself, tree seedlings become adult trees, but tree seedlings are displaced by grass, but grass is displaced displaced by adult trees. So it's like these games in which you have three states, no? Scissors, paper, and rock and pebble. This kind of, so the modeling itself is interesting. And then the parameter space on these parameters, which are the capability of colonizing new vegetation, new area by part of the grasses and the ability of colonizing by part of the tree seedlings. Notice that these B1, B2, B3, which are the dynamical variables, represent the fraction of area covered by vegetation, not the biomass. Okay, it's the fraction of area covered by vegetation. So this is just, then we can talk as much as you want by the details, which need to be discussed. But this is the interesting thing. So take a planet with a distance which is 1.04 from the star, and then you see the H is the habitability index, how much of the fraction of that planet is covered with liquid water, can be covered by, liquid water can exist. And see, this is the distribution as a function of latitude without vegetation. And this is what would happen with vegetation. So vegetation somehow is pushing the outer limit of the habitable zone. Well, it's pretty obvious because it decreases the albedo, but it builds its own niche. It's a bit Gaian, okay, but that is what turns out. So the limit of the habitable zone depends not only on the climate, but also on the fact whether there is a vegetation, whatever vegetation means in that context. So this brings to the last slide, which is there are, well, in my opinion, discovering life beyond Earth is one of the most important challenges that we may face in the coming decades or centuries. Not on Mars, because there is a lot of exchange of material between Earth and Mars. So it doesn't mean, it would be very interesting, but it doesn't mean necessarily anything, because up to now we have only one example. And so there's a lot of debate on this. This nice book is Rare Earth, which basically claims that bacteria or prokaryotes can be very common in the universe, but complex life, no, not at all. So that is the conclusion of this. It's a very nice book. On the other hand, you have the Gaian view that says that once life starts on a planet, it takes over. I mean, that is the message of Gaia, right? Once life appears on a planet, it takes control of the system. Is it true or not? Who knows? But certainly these are two, let's say, extreme different views. And I think it's really one of the big challenges that we have to face. And the other one, on Earth, there is a lot of splendid work on how to generate the first molecules, self-replicating molecules, but from the molecules to a functioning cell, there is still a lot of road to cover. Thank you very much.
Thank you, Antonello. Questions, comments? I have a curiosity myself. There was a view graph, yeah, back where you were showing the two slides where Earth is, this one. What would push this one on the left towards the right? What do you mean?
From that one to this one?
Well, I mean, Earth is not there.
Yeah.
Yeah, okay. It looks like Earth is on the border.
Yeah, this is known, yes.
Right.
Yes, this is known. Earth is on the border because it went to snowball, for example. The first time was probably 2,500,000,000 years ago. The last time was almost 700 million years ago, but it went through snowball many times. So it is close to the outer edge. This is a disaster because this is the runaway greenhouse. I mean, if you go there, goodbye. I mean, the water evaporates, it photodissociates in the high atmosphere that you become dry as Venus. But this one can be pushed, and vegetation could push it. For example, one of the reasons why snowball did not happen after 700 million years ago, well, one is that because the continent, by chance, were not all put at the equator, as they were then, with this supercontinent called Rodinia that was there. But the other thing is that after that, vegetation started to colonize the land, the continental land, changing the albedo a lot, making it much darker. It was granite before, and granite is very light. So vegetation changed the albedo, has a different reaction to the hydrological cycle. So there is the claim, unproved claim, that the fact that the vegetation is on continents would damp this instability. And this is just having a much higher partial pressure of CO2.
Sometimes people talk about terraforming, for example, in Mars. For example, also Elon Musk pushed again this strange idea. You can say it's just a fantasy.
I think it's crazy.
Okay.
I think, yeah.
No,
yeah. I mean, the amount, no, yeah.
I have a question.
Yeah.
Yep.
With your models of the hydrodynamics of the Earth and the multiple interactions and the sun and all of that, and given chaos theory, how reliable are the models that are being developed? Really?
I mean, these
How
models,
predictive are they?
it depends on what models you are talking about. If you're
I'm talking
talking
about
about
any
big
of them.
climate models or these models that I was showing.
Well, not the latter models. The models you began with, you were talking about the predicting a local pattern of drought and whether it's going to be a wet and cool summer or going to be a drought for the summer.
Okay.
How can you possibly predict that given the nonlinearity of the equations and the very short predictability horizon of such nonlinear equations due to chaos theory?
All right. The short answer is that the differences between the position on the attractor and the invariant measure on the attractor. So when you predict weather, you want to know where you are on the attractor, provided there is an attractor and provided you don't know the dimensionality, can be millions. But when you try to project climate, you are really trying to understand how the shape of the attractor depends on the boundary conditions. So it's two very different types of prediction. Ed Lorenz, who was one of the founders of chaos theory, distinguished between predictions of the first kind, you want to predict where you are on the attractor, and predictions of the second kind, you want to predict the general position of the attractor depending upon amount of CO2, characteristic of the land surface. So this is the short answer. The long answer could take half a day, but I will try to make it shorter, is that the big climate models have been shown to be able, I'm not doing big climate models, okay? I'm doing these small things. But I've been shown to be able to reproduce the last 100 years, more or less, or the last 1,000 years. And also to predict the last 20 years if they are tuned on the previous ones. These at large scale, but they have various troubles, and the two main troubles are, there are variables that are very difficult to predict, precipitation, hydrological cycle in general, and second, there is it becomes more and more difficult as you decrease the scale of the prediction. I mean, at continental level is fine. At national level, it starts to be difficult. At regional level or city level, no way. Given this, you still can extract interesting information, but it has to be taken with great care. This is for the long-term predictions. Then there is this realm of intermediate predictions, which is very interesting, it's very useful, but it's very difficult. People can do weather predictions because they do assimilation of the data. Probably you know that every 6 hours, the new data coming from satellites, the network are assimilated and correct with very refined methods, the trajectory of the model. And then people talk about the assimilation method, the kind of using breeding vectors, singular vectors, a lot of technicalities, which is Lyapunov vectors, how you correct your trajectory. But this can be done, and people do this. When you go to much longer times, you cannot do that, because so the frontier now for the big models is seasonal prediction, a few months. It's crucial to know whether it will be a rainy or dry summer, cold or warm winter, and so on and so on. This is still in its infancy. It works quite well in the areas dominated by El Niño. It has a period of 4 years, so yes, it is. It doesn't work well in other areas at mid-latitudes. It does work well, and nobody knows why, in the North Atlantic Ocean. And that is really, there is a lot of work on that. The second point of the big models, the second danger, is that these big models are very much damped, very much dissipative. So they can project almost in a quasi-linear way what is happening today. And that's fine, because if you have 3 degrees more, over 300 degrees, it is a quasi-linear projection, okay? But it's not necessarily true that they get the bifurcations correctly, the collapses of something. And this is what, there is a lot of work again on that. So what I'm saying is that don't trust people who say my model says this and it's better than reality, but there is a huge community trying to make them, well, to work at least reasonably. I don't know if I answered your question.
No, you did a very good job on a very difficult subject.
Okay. Thank you.
Thank you.
Other questions?
Curiosity. The big model, how many variables have? 1,000 or million?
Millions. Tens or hundreds of millions. Now, you know, in the big models, there are 2 big issues. You know the equations for the atmosphere, sort of, for the ocean, sort of. I mean, Navier-Stokes plus thermodynamics. But you cannot reach a resolution where, I mean, you don't resolve turbulence. So you have to decide what's happening below your resolution. Parameterization of unresolved dynamics. In certain cases, it's okay. I mean, 3D homogeneous isotropic turbulence, more or less, you know what to do. But convection, for example, moist convection, you don't really know what to do. So this is the first thing. The second thing is that you have to parameterize processes that you don't know much about it. I mean, the equations of a forest, you don't know them. So you have sort of to invent it or to make empirical. So